wanted to do the last two examples that I had planned on doing for independence, so I thought I'd go ahead and just put them in a video so that you can see again what we were talking about, how to do these problems. So let's look at this 8.2-11. They have students that are divided into categories of how they rank their roommate, and then their grade point average for that first year. So I did not type in this data correctly. That should be an 8, clearly. All right, so here's the data typed in here. They already had the totals here for you, but I'm going to use Excel to get those totals like we did before. So remember, if we want to test for independence, we want to see if the probability that you land in this specific cell, say, is the same thing as the probability of landing in this column times the probability of landing in this row. That's our independence. The probability of the intersection is the product of the probabilities. All right, so these are our observed values. Let's total up the rows and the columns. So just do the sum of the rows and copy that cell down. And now let's go over here and do the sum of the column. So that way, and copy it across. And if like I said, if I typed my data incorrectly, those numbers should all match. And we should get an overall total of 200 here. All right, so let's do our expected table. I'm not going to bother with putting the labels on there. It might help you to keep it organized, and you're more than welcome to put the labels on there. I'm just going to be lazy and not do it. So remember, for expected, I want to the probability that we land in here is going to be the probability that you're in this row times the probability that you're in this column. So remember to do that, and then we multiply it by the number to get the expected value. So to do that, we'll do the total, which is over here. So that's our F7 times, then we'll do probability. So this would be this one, and then I don't want the row to change when I copy this one, divided by the total, and make that absolute. And then do the same thing for the other one, this one, and I don't want the column to change. No, I don't want the column to change, I want the row to change. This one's not right. I want the row to change, sorry, the column to change, but not the row. I said it backwards when I did it earlier. And then divide this by the total. And again, absolute cell reference. Now, like I mentioned in class, notice that you're always going to get an n here that's going to cancel with an n that's in the denominator. Because when we do our expected value, I have to do the total here times the probability. We're assuming, the null hypothesis says assume they're independent. So I calculate the probabilities by doing the multiplication, but we're estimating the probabilities by the totals in the table. So you're going to have an n in the denominator every single time. So if you want to save yourself some typing, or just set up a spreadsheet and fill it in when you're done, have your first cell set up, and then you can copy and paste it everywhere. I'm just going to cancel out one of the n's, so then I just have this B7 cell times this F2 cell, and then divided by the F7 cell. You could have something general set up for the first one. You might have to change the numbers depending on how big the data set is, but in general, this is what it's always going to look like. So if you have a default sheet that you can put some stuff in, you could just change this formula maybe just a little bit before you copy it. All right. So now I need to go over, there are 4 columns and there are 5 rows. So pull that down. So I have my 4x5 table that matches, 5x4 table, which matches this 5x4 table. And now we're going to do our computation, our observed minus our expected squared divided by our expected. Observed is 8, and the expected was 3.6-ish. Squared divided by the 3.6-ish. And then again, I need to make a 5x4 table. So there are all of our computations that we need to put in the table. We will do the sum of all of these That's our test statistic. Let me label that for you. I want the critical value. Do the chi-square inverse dot right tail. We'll use the 0.05 for our alpha, which it tells us now degrees of freedom. Remember, it's rows minus 1 times columns minus 1. So 4 times 3 is 12. So given the relationship here, we would reject H naught. And we can get an approximate p-value again by using our chi-squared distribution dot right tail function of the input and 12 degrees of freedom again. So we've got a p-value of 0.02, so pretty confident that these are not independent. So basically, what this is saying is that if your roommate is kind of cruddy, it might affect your GPA, basically is what that's saying. So the 1 is someone who's difficult to live with, and a 5 is someone who is congenial and encourages scholarship. So you can kind of see, just by looking at these numbers from top to bottom here, that there probably is a relationship between having a bad roommate and having a bad GPA, essentially. So that's what's going on here. All right, let's do the last one. This one has us doing several hypothesis tests. I'm not sure I left enough room for what I wanted to do, but we'll call it good here. All right, so for each of these again, I need to do the sum of the rows and copy that down, and sum of the columns and copy that across. And I'll do it for each of the other ones. That one at least I can copy because it has the right row across. This one I'm going to have to retype because it only has 2 instead of 3 in it. So this one I can pull across. And those numbers all match. This one I can be clever because there are 3 rows in this one. So I can actually grab this sum command that I had up here and it'll do it correctly. All right, so there's our observed tables with all of the sums taken care of. I need my expected tables here. It's just got just enough room to put these in here. So to get your expected, I'm going to do the total. Well, that's not the total. I'm sorry. I'm going to do this column. I want the column to change, but not the row. And then I bumped it. I want the column to change, but not the row. I'm going to multiply it by this number up here. I want the row to change. I just did that backwards again. No, I was right. I want to go across. Sorry. I want this one. I want the row to change, but not the column. And I hit some funky thing, and it's going crazy. I don't know what I hit. It completely closed my file. That was nice of it. What did I hit? Back to what I was doing. It was auto-saving, so we'll see if it actually auto-saved. It did. Okay, back over here. Try this again. All right. I have this cell. This cell, I wanted to make the row change, but not the column, and then divide it by the total. And I want the whole absolute cell reference on that. So let me get back in here again since I messed that up. I had to reopen the file on you. All right, so this is the column, the B5. The B5 here. I got the absolute cell reference on the row because I don't want the row to change when I copy it. I've got the cell E2. I got the absolute cell reference on the column because I don't want the column to change when I copy it. Divided by the total, and I don't want the total to change, period. So I got the absolute cell reference on both of them. Okay? All right. Now I can pull across and pull down. This one, do the same thing. Here's my column. And multiply it by my row. And divide it by my total. And pull it across and pull it down. Last one. Now this one, notice that this table has the same size as this table, so I'm going to be really clever. I'm just going to copy this whole thing. Nope, that won't work. Sorry, because I've got absolute cell references in there. Sorry, this is going to be clever, and I can't do that. Don't do that. Here we go. That column, that row, divided by that total. Oops. What the heck just happened? That row divided by that total. And now copy across and copy down. All right, so those are our expected. So here next door, I'm going to do my, let me just move it up. Just, yeah, do it here. Do my observed minus my expected squared divided by my expected. I'll do this minus this squared divided by that. Pull and pull. All right. Equals that minus that squared divided by that. And then again, pull and pull. This one I should be able to copy the whole thing down because everything is in the same relative position down here as it is up here. So I should be able to copy and paste and get what I need. So I don't have to retype everything. All right. And now for each one, we need a test stat. You write it above it. A test stat and a critical value and a p-value. All right, so the test stat again is the sum of these. Critical value, chi-square inverse, 0.05 with how many degrees of freedom? 3 categories here, 3 categories here, so 2 times 2 gives me 4. And if I calculate the p-value, I get a really, really small p-value. That's a very, very small p-value. So definitely your age and your how you take in your news and what you think your credibility is are definitely not independent. Okay. So in particular, if you look at the table, the under 35s tend to believe television more, whereas the older 54 plus people prefer the newspaper. Okay. All right. Same thing here for the second one. We will do the sum of the elements in our table. We will calculate our chi-squared inverse. Degrees of freedom here is 2 because we have 1 going down and 2 going across. Remember, we subtract 1 for each of those. And again, if we can do we can do a p-value on our test statistic on 2 degrees of freedom. Notice in this case, that's pretty small as well, not as small as that one. But again, we would reject our null hypothesis and say that being male and female are not independent, or sorry, being your gender and how you consume your news, whether or not you believe it, are not independent. And then finally, we can do the last one here. Test statistic is the sum of these. Critical value, our chi-square inverse, 0.05 is our alpha. Back to 4 degrees of freedom again, because we have a 3 by 3 table. P-value on our test stat on 4 degrees of freedom is 0.02 again. So once again, we would reject our H naught and say that the highest level of education also is not independent of how believable someone believes the news is. So hopefully this gives you a little bit of a better idea of how you can do these problems. Again, in all three of these, your conclusion would be would be reject H naught. The variables or the attributes here are not independent. All right. Until next time.